those questions in the chat. So next up, it's my pleasure to welcome Carlo Maria Scandolo from University of Calgary, and he will be telling us about dynamical entanglement. So Carlo Maria, please, the stage is yours.
Yeah, hello everybody. It's really my pleasure to be presenting here, and hopefully soon there will be a version of QPL that will be in person, so it will be the opportunity to meet again all of you in person. Anyway, so this year I'm here to present my talk on dynamical entanglement and the definition.
Sorry to interrupt. We don't see your screen.
I'm sharing it now. Can you see it?
Okay, yeah, perfect. I can see it. Thanks.
Yeah. I'm here to present my talk on the resource theory of dynamical entanglement. So essentially entanglement that's upgraded from states to channel, and this work was done in collaboration with Gilad Gur, also at the University of Calgary. Okay, so let's start without further ado. So why do we care about entanglement? Well, of course, because entanglement is a resource and it allows us to do several things that otherwise would be impossible, like teleportation, dense coding, and so on. So for this reason, we need to identify what essentially entanglement is useful for. In this case, we see that entanglement allows us to overcome sort of locality constraints. I use these quotation marks because it's not, I mean, I'm using locality in a very loose sense, in the sense the ability of doing actions locally in a certain region of space-time, let's say, without much precision in what I'm saying. And again, being a resource, then we can study it with the framework of resource theories. So in every resource theory, again, we need to identify which operations are allowed given the constraint we have. So we have a locality constraint, therefore, what we consider are what we call LOCC protocols. This is, again, standard entanglement theory. So what's the deal with these LOCC protocols is that essentially we can only perform local operations, so into regions of space-time. And then we can exchange classical communication. So we have two parties, Alice and Bob. They can do stuff locally and exchange classical messages. And again, for example, Bob can decide what operation to perform based on the outcome of a measurement or a test performed by Alice. So more or less what is described in this scheme here, where the dash arrows represent the classical communication exchanged between the two parties, and the superscript essentially in Bob's side denotes that the choice of Bob's operation depends on the outcome Alice got, and which was communicated through the classical channel between the two parties. So again, since entanglement has to do with sort of locality constraints, restrictions, we can say that LOCC protocols are the natural way to study the resource of entanglement, their natural setting. Unfortunately, despite being very physically motivated, they're very hard to study. And I like to quote this paper here by Chitambar and others, then, where I like the title of this paper, everything you wanted to know about LOCC channels, but you were afraid to ask. Right, so that denotes the difficulty that lies behind these types of channels. So for this reason, people have developed other types of operations, which are more general than LOCC channels, less motivated, but easier to deal with mathematically. And in this way, we are able to derive some results with much less effort. In particular, and this is what we are going to focus on in this talk, we consider PPT operations. So here I'm presenting the standard version introduced by Rains of PPT states and PPT channels. And I like to, let's say, to recommend paying attention to this slide, because essentially this will be key to the generalization we are going to do to define PPT superchannels in order to study the resource theory of dynamical entanglement. And formally, it will be the same. So what happens in the resource theory of PPT entanglement? Essentially, we have that the free non-resource objects are PPT states. And what does it mean? States that have a positive partial transpose, that's the acronym. So how do we define this? We introduce the transpose operation, we apply it to half of a bipartite state, and we say that a state is PPT if the resulting state after the application of the transpose operation is still a valid state. So free operations instead are PPT channels. How do we define PPT channels? Well, they are defined in the following way. So if I have a bipartite channel and share between Alice and Bob, and we'll go back to this issue later in the talk about what I mean by bipartite channel, but you also saw it in the previous talk. Essentially what we do here, we apply apply the transpose operation to Bob's side at the input and at the output of Bob's side. So let me unpack the notation here. So in analogy with the notation of a state, then also bipartite channel is denoted with the subscript A, B, so Alice and Bob. But now A and B are systems made of two parts, essentially, because there is an A0, which represents Alice's input, and there is an A1, which represents Alice's output, and similarly for B. So in this case, see, T sub B0 represents the transpose operation applied at Bob's input, and T sub B1 is the transpose operation applied to Bob's output. Okay, so in other words, I have bipartite channel, I pre and post compose it with a transpose operation, and if I still get a channel, then my channel original is a PPT channel. Unfortunately, again, this is way simpler than the theory of LOCC, but we pay a price, and the price is that this theory is much larger in terms of sets. So in the sense that now some PPT states are entangled, and again, in Gdansk, they discover that essentially this is associated with the phenomenon of bound entanglement, and we're going to talk about it even later in the talk. Okay, so now after this introduction and brief recap on the issues of static entanglement, which means static for, which means entanglement for states, now we are going to move beyond the entanglement for states and towards, let's say, the entanglement for channels. So why do we care about that? Because in the most paradigmatic protocols like quantum teleportations or dense coding or others, essentially what happens is that we are using entanglement to simulate a channel. So essentially what we are doing, we are converting a maximally entangled state into a channel. In this case, in the case of teleportation, the identity channel, the identity quantum channel. So in other words, we want to see how entanglement interplays with channels, which are called dynamical resources because they transmit information. So information is not static, but it's sort of dynamic. And to this end, if we want to manipulate dynamical resources, which means channels, what we need to do, we need the framework of superchannels, the framework and the structure and the properties of superchannels. So what are these things? So in this talk, to denote superchannels or supermaps, I'm going to use Gothic characters to distinguish between channels and maps, where I'm going to use a script. So what's a superchannel? It's a linear map, first of all, that sends quantum channels to quantum channels in a complete sense. What does it mean? That if I have a channel, bipartite channel N sub RA, where R is a reference system, and I apply the superchannel only to half of this bipartite channel, which means to the Alice's side in this case, and on the reference system I don't do anything, then I still get a channel out of it for every choice of channel N as input. Another notation I'm going to use to distinguish between the input of channels, states that are input in channels and channels that instead are input in superchannels, I'm going to use a square bracket like here to denote the action of superchannels onto channels. Okay, so that's basically what it is. So this definition is a bit abstract in the sense that, okay, that sounds good, but is it anything that we can actually do and perform in a laboratory or in a concrete setting, or is just for, let's say, mathematical entertainment? Well, the answer is that it's not just for, let's say, mathematical leisure, but they are really something that we can realize in a laboratory. And in particular, we can realize every quantum superchannel in the following form. It's enough to take two suitable quantum channels, F1 and F2, which are connected by a memory system E0, okay? And we leave a hole in the middle here. If you see my mouse, I'm indicating it right now. So in the hole between A0 and A1 it's the place where I'm going to plug in the channel in which the superchannel acts. So such a structure is called one cone, and the term one derives from the fact that there is one hole here in the middle. And later on, at the very end of the talk, I'm going to talk about n cones because they are useful for talking, let's say, about distillations of channels, of entanglement out of channels. Okay, so the question is, how do these things interplay with, let's say, a resource theory? So if we take F1 and F2 to be free operations in a resource theory, what we are going to get is a free one cone, which gives rise to a free superchannel. In particular, a channel that can be realized in that way is what we call a freely realizable superchannel, because it admits a realization which only involves free operations of a suitable resource theory. But, I mean, although these freely realizable superchannels are the most physically motivated, again, we can also take a more relaxed approach and, for example, consider completely resource non-generating superchannels, CRNG for short. So what are these things? So as, let's say, as their counterpart for states, these completely resource non-generating superchannels send free channels, so free objects to free objects in a complete sense. In this case, free channels to free channels in a complete sense. This is a very nice and concise definition, but there are some, let's say, interesting developments related to that. So, for example, we know that by the compositional properties of resource theories, freely realizable superchannels are CRNG because they send free operations to free operations. But what about the converse? So is it true that every completely resource non-generating channel is also freely realizable? The answer is that we don't know, and we think that this is actually quite a big problem, open problem in the study of resource theories of entanglement. Okay, so the thing is that these CRNG superchannels, despite maybe not being so physically motivated from that point of view, because we don't know whether they can be realized as a comb of free operations, what happens is that they are actually sometimes easier to work with, as we are going to see, let's say, in the following of the talk, where we are going to study precisely this type of channels, of superchannels, sorry. Okay, so after this introduction on the transition between the static resource theory of entanglement to the dynamical theory of entanglement, then let's see what we do with this dynamical theory of entanglement. Again, first of all, we study the resource theory of LOCC operations. And the object now is upgraded from a bipartite state to a bipartite channel. So what is a bipartite channel? As you saw also in the previous talk, we have a channel where we can identify 4 regions of space-time. Let's say we have a space division between Alice and Bob, and we have a time division between input and output of each party. So this is precisely what we have. So we have Alice's input, Alice's output, Bob's input, and Bob's output. So this is the object we are going to study, and we are going to want to transform using free superchannels. So first of all, we consider the most physically motivated choice of superchannels in the resource theory of dynamical entanglement, and these are freely realizable LOCC superchannels. So let's see what they look like. So again, we have our bipartite channel NAB, which is plugged in the hole here, right? Because here there would be a hole. Then we have a pre-processing, the F1 as in the previous slide, which is LOCC, and a post-processing that is LOCC. And here also the memory system is split into two in order to take, let's say, to recognize the fact that actually we have two parties that are, let's say, space-like, that are, let's say, separated in space. Okay, so this looks nice, but the problem is that these objects are hard to work with because they're already hard to work with in the static case. You can imagine what happens in the dynamical case where, I mean, if you want to study this transformation, you have to consider not one, but even two LOCC channels to be combined together in this way. So again, the standard problem of resource theories is always to study if I'm given two channels, N and M, if I can convert one into the other. So to this end, we developed actually a complete family of monotones that are able to answer this question. So suppose again, I want to consider, I have two channels, N and M. So for each of these channels, so in this case for N, we define a family of monotones, which is defined as follows. So we take any channel P, A prime, B prime, where A prime, B prime is essentially the system on which the other, let's say, channel acts, okay? The other channel M, A, B. You'll see later what I mean by this. Then we define these monotones E sub P because how do I construct this monotone? I take the Choi matrix of P, which is denoted by J. I consider the Hilbert-Schmidt inner product of this Choi matrix with what? With the Choi matrix of the action of a generic LOCC channel on N, so on the channel I want to consider. So I take all possible LOCC superchannels, sorry, because you see it's Gothic and square bracket. So I take all possible LOCC superchannels, I apply them to N, I take the Hilbert-Schmidt inner product with P, and then I take the supremum over all these possible values, and this gives me the value of this monotone here. So it turns out that this monotone can be calculated using a conic linear program, but the conic linear program is actually hard in this case because we are talking about the cone spanned by the topological closure of LOCC channels, which is actually a very hard, this is a very hard cone to deal with. Okay, so, but we are still able, I mean, in principle, if we are able to calculate this family of monotones, we can actually prove this theorem. Essentially, we have that the channel NAB can be converted in a topological closure into M, A prime, B prime, if and only if for every channel P, these monotones, okay, the monotones applied, the value of the monotones on N is greater than or equal to the value of the same monotone on M. If this is true for every channel P, then we conclude that a conversion is possible. We can also approach the conversion problem from another point of view and using the technique of the conversion distance. So what happens in this case? So here, again, I take all possible LOCC superchannels, I apply them to NAB, and they will give me some output, and I evaluate the distance from the output from the target channel M. And the distance is evaluated using the diamond norm. And finally, I take the infimum over all possible things in order to evaluate the smallest possible distance I have. Again, we can convert into N into M using the topological closure of LOCC if and only if this distance is 0. And this distance also allows us to calculate, let's say, a conversion with error where there is some epsilon, for example, because there is the notion of distance that is built in. Again, calculating this conversion distance is a conic linear program, but since we're still dealing with LOCC superchannel, this is actually a hard one. So for this reason, again, we want to simplify what happens in those, let's say, in the theory of entanglement. So we enlarge the set of free operations, and instead of considering freely realizable LOCC superchannels, we consider PPT superchannels, which give rise to an easier resource theory. So how do we define those channels? Again, remember that for PPT states, I started with the transpose map. Now here I start with the transpose supermap. What is this transpose supermap? The transpose supermap is applying the transpose to the input, the one with subscript 0, and the output, the one with the subscript 1. Okay, and again, we can say that in the same fashion as we did for states, a channel is PPT if if this transpose supermap applied to both sides is still a valid channel. And similarly, remember that we defined earlier that a channel was PPT if we could consider like the transpose, pre-composing and post-composing a channel with a transpose map. Here now we pre-compose and post-compose a superchannel with a transpose supermap. If we still get a valid superchannel, then we find that we say that the superchannel is PPT. Okay, so what can we say about PPT superchannels? Well, PPT superchannels are CRNG for PPT channels. So they preserve PPT channels in the complete sense. They are a superset of LOCC superchannels. And now, if we apply the same constructions we saw earlier, where instead of optimizing over LOCC superchannels, we optimize over PPT superchannels, we get that the previous conic linear programs become SDP, so much easier. So both in terms of monotones, the complete set of monotones, and also in terms of the conversion distance. So this suggests that actually, if we study monotones for NPT entanglement, we can also find monotones for LOCC entanglement because of the inclusions. And maybe the monotones for NPT entanglement are easier to construct and compute than those for LOCC entanglement. So this is what we are going to do now. So the first one we introduce is the negativity of a channel. The negativity of a state was introduced by Vidal and Werner, and it's defined as you can see here. So it's kind of easy how to translate this definition into the analog definition for channels. So we replace the transpose map with a transpose supermap, and we replace the one norm with a diamond norm. And this is what we get. Okay, this is our hint, but then we are also able to prove that this, let's say, this new negativity for a channel is actually well defined because it's actually a monotone in the resource theory of NPT channels, and the proof is actually quite simple, but I won't report it here, and it follows from the properties of PPT superchannels. Now, this one I'm going very fast because I can tell you that despite the resource theory of NPT being simpler, sometimes the monotones can be rather savage in their definition. So look at this. So we define this max-logarithmic negativity, which is defined through this kind of complicated expressions where we have the various constraints. Again, J denotes the Choi matrix of the channel. So I don't want to spend time on this, to be honest, because I just want to show you more or less what it looks like. And the funny thing is that this is also computable with an SDP despite the hard problem, so the hard definition in which it's defined, and it's also an additive monotone. So if I have a tensor product of channels, then this will be additive on that. So why did we introduce this funny looking monotone? Well, because it has an operational meaning. The operational meaning as follows. So we want to prepare n copies of a certain channel out of some copies of the maximally entangled state, only using PPT operations. So that's essentially, this is what we want to do. Right, and that's the scheme. So
you have about 1 to 2 minutes to go.
Yeah, I'm almost done. Yes,
okay,
indeed. So what we see here is that again, we have sort of a cost-like type of experiment, let's say, protocol we have. We require that the conversion is exact for every n. And what happens is that if when I take the limit as n goes to infinity, that the cost I obtain is precisely given by the funny looking monotone, the max logarithmic negativity. So after the cost, we have the we can study what happens with the distillation. So how we can get entanglement out of many copies of a channel. In particular, we want to see whether we can achieve distillation out of a PPT channel. We know that for PPT states, this is not possible. But for channels, the situation might be trickier, because what happens for channels is that when I have n copies of a channel, it doesn't mean that I can compose them only in parallel. I can compose them also in a more complicated way through an adaptive protocol where I insert n copies into the slots of an n comb that has n holes where I can plug in my n copies, like in this case. So in particular, we are interested in a PPT comb. Why is that? Because PPT combs, again, also include LOCC combs, and if I can prove that the distillation is not possible using PPT combs, then it's not also possible with LOCC. So what's a PPT comb? It's a comb where if I compose all the channels from E1 to E sub n plus 1, I obtain a PPT channel. Again, so this is the most general distillation strategy. It's simple, but we can get upper bounds, and indeed, we get that it's not possible to distill entanglement out of PPT channels using any possible sort of strategy, even if adaptive, and this follows from the properties of PPT combs. And again, this allows us to show that, in principle, we have bound entanglement again even for the case of channels, not just for states. So to conclude, so what we did, we developed a rigorous and systematic approach to entanglement for channels. In particular, we focused on simpler situation, MPT entanglement. We derived measures of dynamical entanglement. We found bound entanglement, and essentially we found some bounds also for other interesting resource theories. But now what's left ahead? Essentially, the whole area of dynamical entanglement is yet to be explored, because there are still open questions. So what happens to the LOCC theory in the dynamical case? Is it possible to characterize it? So again, what can we say about multipartite entanglement? And again, what measures of dynamical entanglements are available in this case and are meaningful? So I leave you these questions as let's say, ideas for future research and for the whole community. And with that, I'd like to thank you for your attention. And here I'm giving you some references.